All right. Welcome, everybody. I wanted to welcome you to today's webinar on mastering FEA meshing techniques for thin-walled assemblies. Today, both David Weinberg and myself, Andrew Jabola, are going to be presenting on some topics of looking at different meshing types for thin-walled type structures. So the first thing, let's go over the agenda of what we're going to be covering today. First of all, before we get started in the meeting, we're going to give a background of Structures.Aero and SDA software and who we are and what we provide to our customers. Then after that, David Weinberg is going to discuss challenges that you might run into in the meshing when trying to choose the right mesh type for different structures. We're going to be looking at shell elements versus solid elements in FEA and the disadvantages and advantages of this. After this, we'll do a demo highlighting some of the capabilities in FEMAP to be able to control your different mesh types for all sorts of situations. So let's first of all give a little bit of a background of our company. So first of all, who is Structures.Aero? Structures.Aero provides a lot of aerospace consulting for both design and analysis, and we're a services arm. We consist of 23 engineers, and we focus a combination of aerospace and mechanical engineering. One of the key things about our company is that we use the products that we sell on the SDA software side. So day in, day out, 10 of our engineers who are analysts use FEMAP with Nastran every day for our work. So when you call us for a question, not only are we able to support your software, but we're actually able to answer those questions with industry experience backing up that knowledge. So we might be able to help you not only on just the button clicks, but also the actual usage or ways you might want to handle different product lines. Just to kind of discuss some of the projects of that Structures.Aero has done. We cover a wide variety of industries, focusing quite a bit on the space and aircraft side. On the space side, for instance, the composite crew module, the Roman Space Telescope, New Glenn for Blue Origin are some of our space programs, among others. On the aircraft side, we've supported a lot of manned aircraft as well, such as Piper aircraft on the M600, White Knight 2 and Boom Supersonic. On the UAV side, various UAVs such as the Aeroson series from AAI, Aurora's VXP program, and various other programs. In addition to the aerospace side, we actually have supported other industries as well, such as industrial with Hackler dredges and also ground air support, and many others that are not listed here. Our partner company is SDA Software. And so Structures.Aero and SDA Software are essentially one company here that provides the software side of products. So we sell products such as FEMAP, which we're demoing today, NXCAD, Nastran, and SimCenter. Just to name a few, also Star CCM, which we've done quite a few webinars in the past through some of our other application engineers. In addition to this, we provide training for our software, especially on the FEMAP side. So with this, we're able to give your team, not only the button clicks, but be able to introduce our industry experience into your training class so that you're able to most effectively use the software for your needs on whatever application you're working with. So we provide this training, both intro and advanced training for FEMAP, and we also provide FiberSim training. So for those of you who are looking more for looking at composite manufacturing or draping analysis and other aspects of that, FiberSim is another area we support. Also, for existing customers, our software, we directly support this and actually to provide answers to questions such as, if you have a, licensing issues or tech support issues or even general usage questions, we're always here to help and are well connected to the development team. So when you ask us a question, we will go talk directly to Siemens development if we don't know the answer and get those answers as quickly as we can for you. So at this point, we're going to go ahead and hand it to David. And here's the agenda again. So David, at this point, I'll let you take over.
Thank you, Andrew. So today we're going to talk about challenges, shell elements versus solid elements in FEA, disadvantages and advantages of shells over solid elements. Andrew's going to do a detailed demo, and then we're going to have a conclusion at the end. And somebody just asked about the presentation. It will be made available to everybody at the end, so you don't need to take notes or screenshots. We'll give you information about that at the very end. So, challenges. How do you ensure accurate results on a complex geometry while still ensuring reasonable run times? That's a big challenge. What are the most appropriate times to use solid mesh versus a shell mesh? If solid meshing, are 10 solid meshing still relevant today, given the hex meshing technology we have in FEMAP? And what are effective ways of verifying the data generated from your models? So here's a good example of two totally different applications. On the left, we have an engine block. On the right, we have a semi-monocoque structure, a Cessna aircraft. So when to use shells versus solids? I mean, it's pretty obvious here what the answer is, but the components of the structure and how it was manufactured can help you decide what element types to use. So the engine block here is die or sand casted. And in general aviation, aircraft typically are made from sheet metal that's formed to make frames, ribs, longerons, etc. So we would use solid elements for the engine block, and we'd use shells for the aircraft structure. Next. So disadvantages, we'll start with them, of shells over solids. The big one here in the beginning is the thickness assumption. Shell theory assumes that you're dealing with thin structures, and that's because the stress through the normal direction is assumed to be 0. And so it's great. It actually will work with thick shells as well as thin, but you have to remember that. And the complexities in modeling. Setting up a model with shell elements can be complex, especially when defining the orientation of the shell. And when we say that, it's not only just the material orientation if you're dealing with an orthotropic material, but it also deals with the normals because pressures are going to be relative to that contact as well. Or dealing with transitions between different thicknesses. Corner treatments, the treatment of corners, and we'll see this later, and intersections can be problematic because the shell theory doesn't account for three-dimensional stress concentrations and fillets, for example. Boundary conditions. So with those, with solids, it's pretty straightforward, for example, when doing symmetry, but with shells, it's a little bit more complicated. You have to deal with the rotations. Accuracy at thickness discontinuities. Shell elements may not be accurately model the behavior at points where there's a sudden change in thickness, such as stiffeners or joints. And the requirement for expertise. It's really tempting, and this is one of the reasons why with a lot of the FEA embedded in CAD software, you have this TET meshing of a solid. With shells, it's a little bit more complicated. You have to have a little higher level of expertise. Next slide. Advantages. Well, the biggest advantage I'd have to say is the computational efficiency, and we're going to see that in this presentation. We're talking about performance gains of anywhere between 10 and 100 times faster. Accuracy. They're very accurate, shells are, when modeled correctly. In other words, when you use the right element for the right application, they're going to give you a very accurate result. And we're going to show that as well. Reduced degrees of freedom. You're dealing with an element that has, let's say, 6 degrees of freedom per node, 4 nodes, 24 degrees of freedom. Compare that to a TET 10 with 30 or a hex 20 with 60. You can see that it's going to be better, faster. And versatility, shell elements can be used to model structures that vary in thickness. So you can have a structure like a tapered beam or anything like that where every element is a little bit thicker or thinner. They account for that. And they also can handle offsets and also holes and other geometric complexities requiring a fully three-dimensional mesh shells can handle. Next. And now off to you, Andrew.
All right. So what we're going to show here is how we can use FEMAP to be able to generate both solid meshes using the new hex dominant mesher specifically, and then also mid-surface meshes. The first thing we're going to start off with is setting up the model for a solid mesh situation. So here we are, just to kind of show the ease of the product, where this is typically what you are greeted with when you open FEMAP, minus the other models that are open already. First thing we need to do, typically, when you're working with FEMAP is to bring in the geometry. So we're going to go ahead and import the geometry. And one thing we want to indicate here is that FEMAP is CAD neutral. Now, in this case, we're importing a parasolid file. But one thing I want to highlight here is that we can import from programs such as Inventor, Rhino, CATIA, Solid Edge, and so on and so forth, as well as the traditional neutral file exports such as Parasolid and Step. So in this case, we're going to go ahead and import a Parasolid file here. Specify our geometry scale factor of, and this scales from meters to whatever unit system you're using. In this case, we're converting to inches. And here we have the geometry in the model here. Now, typically, one of the first things you do as an analyst is you set up your properties. So the first thing we're going to do is we're going to go ahead and define the materials in the model. Now, in this particular model, we're going to use a isotropic material because this is a 10-foot steel beam with a 5,000-pound load is our eventual goal. Now, we can enter this directly into the modeling environment based off information from MMPDS. One of the nice things that comes with FEMAP is a material library outside of the box, which has quite a few isotropic materials. In this case, I'm going to be using stainless steel 17-4. The thing that we can use these libraries for is that in case you might have a company that has, for instance, a lot of different composite fabrics, and you want to be able to store that data. Instead of always ensuring that you're copying it down and making sure it's synced up between the models manually, you can have a library of that information automatically set up for your users, and then your users can pull from that data instead of directly from the information itself. So see, I saw a question pop up here. There was a question, link material cards MMPDS. You would have to generate that card data library, but once you have that data entered in a, for instance, a personal library, and there might be data out there already. It just depends on your company. You can use that information and have that linked in your model. So here we're going to hit load, bring that information into the model here. And you can see we've automatically entered Young's modulus, mass density, and other parameters that might be useful. So let's go ahead. Now we're going to go ahead and set up the properties. In this case, we're just using solid elements. Now, one thing to highlight in FEMAP is the FEMAP supports a lot of different element types. You have a lot more control than maybe some of the other software packages that may only support certain element types. We have the ability to drive beam elements if you're trying to define large truss structures, plate elements, for thin walled structures like we're showing here today, solid elements, and many other element types as well. So FEMAP gives you, the analyst, complete control in that regard to the different areas. So in this case, we're going to be using solid elements because we're going to be demonstrating the hex mesher first. Here, we're going to specify the material, and we'll define our properties. So I'm going to define one for the beam, I'm going to define one for our supports, and one for our load application. The next thing we're going to do is we're going to go ahead and set up the boundary conditions. Now, FEMAP gives you the ability to organize these very cleanly in your model info tree here. So if we just right click, we can create a load application boundary condition and a constraint. Container or set. Now, again, FEMAP allows you to organize these, and many programs will have hundreds of these that can be organized, and there's lots of ways of being able to work with that data inside the FEMAP database. So the first thing we're going to do is we're going to go ahead and define a fixed boundary condition, and so we're going to apply this on the surface on the bottom of the structure. So I'm going to grab this surface and this surface as well on the structure. So we're going to go ahead and fix that. Next thing we're going to do is we're going to go ahead and apply a 5,000 pound download on the surface. So here we'll select this top surface and we'll apply 5,000 pounds on the bottom, on top of that surface as well. Now, sometimes you may want to add other boundary conditions, such as maybe symmetry points, or maybe you have a pad that is loading on your structure that may not be modeled. FEA gives you the ability to modify your geometry, and we're actually going to highlight this tool in a lot more detail on the mid-surfacing, and then also potentially in future webinars as well. So here we're going to show the meshing toolbox, and what we're going to do is we want to add a X constraint along the lines of symmetry here to help restrain the structure. This helps reduce solve times tremendously, or might represent, maybe a bolt or something else that is preventing the structure from sliding in the X axis here. So here we're going to go ahead. I'm just going to break at the midpoint here, this curve. So turn on geometry editing. This is the meshing toolbox, curve break. Grab this curve. I'm going to split up here and then down here. And then I'm just going to create a new edge by going from the point to the edge where it splits from this point normal to that curve. And we'll do the same thing on the bottom surface here. This gives me the ability to go ahead and add a small constraint on the model. So I'm going to add on curve. So I'm going to put a constraint here and a constraint here. And we'll go ahead and do an arbitrary incissus in the TX direction. So that, again, we're restraining the model, sort of a pseudo-symmetry condition. And at this point, we've actually set up the model for meshing outside of contact. So the next thing we're going to need to do is define the contact between the model here. Now, we could do this manually. This is all handled under the connections section of the model. But here, we're going to go ahead and use the automatic contact. So here, we're going to say, I'd like to detect contact between these solids here. Here, we can specify the tolerance. Now, our CAD happens to be touching, so we're fine with the defaults. We'll specify the connection property. And what this automatically does is it specifies your property, your regions. So here we have a support region, the bottom of the beam, the other support region, the top of the beam, and the load application, and your connectors that connect the support and the top load application points on the model. We're going to do a couple other one quick modification to help for stability of the system. We're going to go ahead and add a 0.2 friction coefficient. And many of the other settings here, if you have questions on this, we can definitely go over this in future webinars or through direct contact to us. We're going to hit OK. So at this point, we've actually defined all the boundary conditions, and we are ready to go ahead and mesh on the model. Now, in the past, complex geometry like this could either only be tet meshed, which required many elements through the model, or if you wanted to hex mesh this, it'd be hours of splitting the geometry, trying to make sure everything was extrudable and connected, which could take hours, if not days, even for simple geometry like this. But since version 2022 of FEA, the hex dominant mesher has essentially become a replacement almost for the tet mesher inside of FEA. To get to this, we go to hex mesh bodies, specify the bodies we wish to mesh. And here we now have the hex dominant auto mesh bodies command. So let's just go over a couple of the commands in here that are pretty relevant. So the first thing is, of course, the target element size. So what this is going to do is it's going to try and target a hex element size that meets, this target element size here of 0.15 inches in this case. Here we can use curve sizing. So if there's existing curve data on the model, it will try and use that sizing. We could try and size to all the curves, which would end up constraining the model to the most. But the defaults here are actually great with the required curves only. This will go ahead and only size to those curves. And what it will do is it attempts to create the cleanest mesh possible while still maintaining within the geometry, and will select the curves that it believes it needs to be able to size correctly. The other option here is the size surface of all curves are sized. So for instance, if we have all the curves sized in here, it's also going to ensure that the interior of that surface is also sized to make sure that we get a relatively consistent mesh. On the mesh associativity, the default settings require geometry only, but sometimes you may want to include little details. For instance, we've added these two curves on the top and bottom that we want to ensure are in the mesh so that we have nodes exactly along that boundary condition. So we can grab additional geometry. So maybe we want to grab this here and this here. And what this does is this ensures that things such as, symmetry lines, you might have a pad up to represent some sort of load on the structure, are included in the mesh, and it ensures that you have nodes along that part of the structure. One other important thing is the additional geometry by angle. What this does is things around such as curves right here, it will actually increase the density of the mesh around those regions so that it ensures that you have more elements. So for instance, around fillets and other items like that, you're going to get a better element count to hopefully capture some of those details in the model. Finally, we have the option for mid-side nodes. So we can either turn this off and we're going to end up with hex 8s, or we can have it mid-side nodes for all elements, or have it all elements but bricks. And then finally, we can also move the geometry, move the nodes to the geometry. So for instance, if you have mid-side nodes, it's going to attempt to move those mid-side nodes to the geometry directly. Now at this point, usually I would hit OK, and we wait about 5 minutes. But in the interest of time, we already actually have this mesh generated. And we're going to actually show the differences between the hex 20, the hex 8, and also tet 10 meshes. So at this point, I'd hit OK. And about 5 minutes later, we would end up here with the hex mesh. So this actually brings us, just to kind of proceed in here, to the hex mesh side of the discussion. So here we actually have the resulting hex mesh. We also have hex mesh the other bodies. Here we have the properties of the beam, the supports, and the load block as well that have also been hex meshed. Now, one thing we want to show is how clean of a hex mesh it has created through here. Again, this has required almost no direct user interaction other than setting up the model and literally hitting run. You can see around here, we transition to try and capture some more of those elements in the corners around here to get a better quality of elements around, important geometry. And that was with that one checkbox we turned on. In this particular case, we have mid-side nodes. So you can see I just turned on the nodes here, and here are mid-side nodes on the model. So overall, we have a very high quality mesh that we can start working with directly. And so instead of spending the many hours you'd spend in past trying to create the perfect hex mesh, you're able to generate a hex dominant mesh very quickly in the model. Now, just to show something from an element count standpoint, we have about 300,000 elements here and about 1.2 million nodes. Here, we're going to go ahead and show the hex 8 version. So this one eliminates the mid-side nodes, and you can see here, now we have essentially the same mesh, but no mid-side nodes. Again, we're about 300,000 elements and 310,000 nodes, so significantly smaller or fewer node count. Now let's go ahead and compare this to the tet mesh. When we tet mesh using the original methods, for those of you who've been using FEMAP for years or many other solvers, to get the equivalent quality or equivalent size of mesh is going to require a significantly higher amount of elements. So for every hex element, we have around 10 elements to get the same number, or 4 to 5, depending on the, where it cleaned up. Here you can see that we have jumped from 300,000 to 1.2 million and almost 2 million nodes to try and capture the TET10 here. So again, we're going to have longer run times, larger output files, and longer run times, especially for a TET10 versus a hex 8. And then also, again, much larger output files because we have that much more data we need to process. All right. So let's go ahead. We've shown a little bit of the differences here. For the final setup of this model, as we come back to the meshing side of things, what we can do to set this up is we're going to go ahead and we would go ahead and create an analysis set. And this is going to allow us to highlight one other thing about FEMAP and the being CAD neutral. It is also solver neutral. So we're able to produce decks for instance, Autodesk Nastran, LS Dyna, MSC, so on and so forth. So we're able to generate this, your decks directly out of the same model. We could even create a model that is run in NX Nastran, have it automatically set up to be run in Autodesk Nastran as well, and be able to run both out of the same model without too much effort. In this case, we're going to go ahead and just show we're going to run a static case for Nastran itself. One of the things we're going to do is we're going to set up the element iterative solver. We'll set up the amount of cores. So, for instance, depending on your system, I might run 8. You have quite a bit of control of your model, whether it's the bulk data options, your geometry check options, your boundary conditions, and your output requests. And in this case, we're going to go ahead and go with the defaults. At this point, we're actually ready to run. If I hit done and I right-click analyze, this would start up Nastran and start running the model to get those results. Now, in the interest of time, we have these results already set up here, and I've attached an OP2 file with the Hex 20 model. All right. So we're going to show a little bit of post-processing, and we're actually going to compare the results between the Hex 20, the Hex 8, and the TET10. So the first thing, though, we're going to show is a little bit of the post-processing capabilities within FEMAP that make it a very powerful mesh. And Colin, to answer your question real quick here on the update mesh sizing locally, you would be able to define the mesh sizing on the curves directly. So in this case, when you hex mesh bodies, I should do it on a different mesh, you're able to specify those curves directly. You'd have to, delete the mesh and then go ahead and update those locations locally if necessary. All right. So coming back to this, the first thing we're going to do is we're going to go ahead and show how you'd start with post-processing. So the first thing we'll do is we'll go ahead and select the contour view. FEMAP, this is sort of the default FEMAP view of what you'll see, but we have a lot of control of how we can show this data in the model. So for instance, we might want to turn off filled edges. A lot of people want to control the contour, and so they really want to change these colors. We can change this on the fly by going to the post-processing levels, change this to no magenta, or you can set up your own color profile as well in the model. And finally, we might want to set up the levels and try and identify a peak stress. So very quickly, we can just double click here, specify a max min threshold. And in this particular case, our limit stress is 25 KSI. And very quickly, we can identify that overall, globally, we show that our structure is passing, but we do have some potential local yield regions around the fillets. We can identify where our max stress is. Maybe we want to turn on the label, and we're just going to turn this on again under post-processing toolbox. You have to expand the levels and the max only, and you'll see this pops over here and we have a 51 KSI number. So again, FEMAP gives you a lot of control on the post-processing of the model and being able to look at the data here very quickly and be able to interrogate your model. Just for comparison, we're going to go ahead and show this on the Hex 8. So I'll turn on contours, turn off filled edges, and you can see here our stress is a little bit lower because this is a coarser mesh or not as a less converged mesh, but the overall profile is the same. We would see the same on the TET mesh as well. So if we go ahead and let's turn off filled edges first and turn this on, turn on the contours, you'll see this is actually one area where the TET mesher might actually be a little bit slower. And you can see here we have the similar contours of the mesh in the model as well in the same location. And we have a slide showing this. We can also show the deformation on the model as well. So we might want to deform the model. Here I have actual deformation turned on. Here's exaggerated. We might want to turn on actual and scale it up to 10. So we've shown a little bit of the control of the post-processing side. We're going to show some more of this here very shortly and some of the other capabilities we have with this model as well. Now, how do all these models compare specifically on stress and also runtime? So first of all, for stress, we're actually showing very similar numbers between the TET 10 and Hex 8. The Hex 20, we show a higher stress, but this is because we have a higher order element, and thus we're probably converging to that stress. I would imagine that if we kept refining the mesh in this region, we're going to end up somewhere around 51 to 55 KSI, maybe a little bit higher, a little bit lower in that region. But overall, we can see that the Hex 8 and TET 10 are almost, or all of these would lead to the same design conclusion. We either need to change the thickness or change the fillet to ensure that we have positive margins in this part of the structure. Now, how do we compare on deflections and runtime? Well, we can see that the deflections of the structure are almost identical. We're within 20 thou across a 120-inch structure. But where this gets really interesting is the runtime in the model. So the TET 10 took 26 or 2,700 seconds. Now you might be asking yourself, why did the Hex 20 take a little bit longer, even though it had less nodes? It's because the Hex 20 is a more complex element. And also there are some capabilities in the element iterative solver that focus on the TET 10 that help speed up that process. But really where the comparison comes in is really between the Hex 8 and TET 10. Both of these models gave us essentially the same answer, but because of the reduced node count and element count in the Hex 8, we actually have a 5x reduction in the runtime. So what can we conclude from this? We could run for a lot of your iterations, you would run your Hex 8 models and get similar results to the TET 10 in 1/5 time. And then when you finally need to refine the mesh and you're interested in those details, you might be able to run the Hex 20 to ensure that you're getting that accurate number. We were already seeing that the TET 10 actually got a similar stress to the Hex 8, but that probably means we were not converged, which means we need many more elements to capture that convergence. Right. So this shows the Hex versus TET. But we've also discussed shell elements. So now we're going to discuss mid-surfacing in FEMAP. This is actually where FEMAP shines, is being able to control your mid-surface meshes. So in this case, we're going to go ahead and restart the model. We're going to go ahead and pull in the same contact block, pull in the same material. Load this. We can filter for it real quick. And we're going to go ahead and generate a single property right now for the beam. And again, we are now using a plane element plate. Specify the thickness, specify the material, and hit OK. So for this particular case, in the interest of time, we're only going to focus on mid-surfacing the beam here. So to generate this, most of the time, the first step we're going to do as an analyst is attempt to use the automatic mid-surfacer. Many times this works, but for those of you who probably worked with any sense of real geometry, probably know that this is not the case. That usually doesn't work on the first try. So here, we're going to go ahead and show the automatic mid-surface. Some of the complexities we're going to have is around these multi-thickness areas. We're going to specify a target thickness. Now we can measure what the thickest region that we're going to look at. And what this does is this looks up to the region of the model and will create a mid-surface up to that distance. So for instance, this large circle here, it will go ahead and create a mid-surface. So we're going to measure this. So this gives us the distance there, and this is kind of why I input the 0.9. We're going to go ahead and automatically mid-surface the part. So if we hide the block, you can see it did a great job on the caps and also some of the supports in the middle or the frames, but it didn't do a great job in the center section. So what we're going to show now is the power of the meshing toolbox and also non-manifold geometry and being able to generate mid-surface models very quickly and easily in FEMAP. So the first thing we're going to do is we're actually going to get rid of the surfaces that it created on the web, since these are probably not going to be too usable for us. What we're going to do next is we're going to turn on the geometry. And one of the things we can do is we can actually go ahead and slice the geometry. So we're going to go solid, slice, and we're going to create a cross-section slice across the center of this piece. So I'll hit OK, cross-section slice with a plane. We could do a curve too if you have some much more interesting size geometry. We'll grab the solid here. Specify the plane for the intersection. So I'm going to locate this using the midpoints of these curves. That's what the mid ID or midpoint means here. We can verify by highlighting to make sure that our plane is slicing through. And here, we'll go ahead and uncheck this, and you'll see that now we have a very clean mid-surface on the structure here. Now, one of the things in FEMAP that was added, and actually quite a while back, is the non-manifold add. Now, in many earlier systems, I think prior to even version 10 or 9, I cannot recall the exact date, you would have to intersect this CAD and make sure that the curve on this side was matched up with this side. But the non-manifold add command is a very powerful command inside the FEMAP geometry editing tools. So in this case, we're going to go ahead and do geometry, surface, non-manifold add. Grab our geometry here. Hit OK. Now we can specify tolerance, and I'm going to put 0.05, and I'll zoom in to show why this is an issue. Sometimes when you mid-surface, and this is no fault of FEMAP, this is just the aspects of our geometry, you might have geometry that is slightly offset from each other and doesn't match. If you were to leave it at default, it would just simply, you would end up with a small little surface, and there are tools to find that, but here we can go ahead and have it where it automatically stitches the geometry together. So in this case, I'll leave this at 0.05, hit OK. And you'll see that little region here has actually been stitched together, so we now have a clean mid-surface. Now we're going to go into really some of the more powerful tools in FEMAP, which is the meshing toolbox. So the first thing we need to do is we need to remove this outer flange from the geometry slice. So we go to Feature Removal, Surfaces, activate the toolbox. and we can zoom in. We're going to grab this surface and remove the outer flange. Now, one of the other things we saw in our solid model, if I go ahead and go back to this, is if we uncheck this, you'll see that our solid model has different thickness changes. And we want to ensure that we have these thickness changes in our model in FEA. So what I'm going to do here is I'm going to show the solid and hide the surfaces, and then use the geometry editing capabilities in FEA to project those curves onto the structure. So here, geometry editing, project curve, and we can use this in print. We're going to actually print, extend, and clean. So this will take the curve, extend it to the edges of that surface, and clean the points that it had. And we can quickly split up our geometry. So here you can see, just by clicking on the surface, specifying the curves, and this time, and I'm going to grab the circles here, it's going to take those curves and project them onto the surface. And now we have a surface that represents that. Let's do the same thing here. We'll grab this surface, grab the dialog select. Here I'm going to grab this curve, this curve, this curve, this curve, and grab all the interior curves that represent our thickness change, so we can capture that accurately with a mesh. So here, even though these curves don't extend all the way to the end, when I hit OK, you'll see that it extends it to the next curve and creates a very clean geometry in the model. We'll finally do the same thing here on this side. Grab these curves, highlight to verify, and extend. We can do other options as well for splitting geometry. We'll actually show that a little bit later here. And at this point, we're actually ready to go ahead and mesh the structure. So the meshing toolbox gives you the ability to very quickly and interactively work with the geometry on the model. So here, we're going to go set up mesh size. We're going to use 0.2, specify our property, and we're just going to go ahead and select our beam elements here. I'm just box selecting by holding Shift and grabbing our model here. I'm going to turn off elements, or just turn off everything and show the elements only. And you can see here, we have our mesh on the model here. Maybe, for instance, we need to add those symmetry lines. Now, the beauty of the toolbox is this actually allows interactivity even with the mesh on the model. You'll see here that if I break this curve, it will go ahead and it says remeshing here, but you're going to see here when I do point to edge, it's actually going to remesh that on the fly, the model. So here I'm just kind of splitting these curves edges up. So I'm going to grab the other side. And very quickly, interactively split the mesh here. We can also do things such as change our mesh sizing. So maybe we want to increase the count on the element here. Like here, we're having a little bit of an issue. Actually, we can turn on the surface mesh quality and kind of take a look at this data as well as we start working with the model. We can decrease the elements on the fly, and you can see here, some of those changes allow us to very quickly modify the mesh interactively. We can also do things like add mapped meshes and change the, now in this case it's already mapped, but we could change that on the model throughout. So the meshing toolbox gives you a lot of capability of interactively working with your mesh on your model. Now, one thing we haven't done is, you saw that when I defined the property, I used a thickness of 0.1. So obviously our thickness does not match the original geometry here. Now, in the past, you would create individual properties and assign your thicknesses, probably spend some time measuring. But FEA gives you the ability to automatically resize the geometry, the elements to the mid-surface. So if we go to Modify, Update Elements, Mid-surface Thickness Offset, grab Mid-surfaces, grab the method on Solid, and hit OK, you're going to see that we're going to actually have all our elements. It's going to modify the element thicknesses locally on that property. And each element is going to have the appropriate thicknesses that we had defined on the model. So you can see here, we actually have the appropriate thicknesses. And since we split up the geometry, we're able to capture that very quickly and easily in the model. Same thing in this region as well. So very quickly, we're able to actually generate a very clean mid-surface model that we can start working with. Now, in the interest of time, we're going to go ahead and just kind of finish up the rest of the cases here. In this case, we've set up the model. We've applied the loads. So I've applied the loads to the top surface. I've applied the constraints. They're fixed at the ends and a symmetry constraint here. We've defined our contact conditions. So here are our connectors for the supports. And here, we've set up our analysis set. Now, the one difference we have in this particular case is that I'm requesting equation force and force balance. At this point, we would hit run, and we could go ahead and post-process. And you can already see that our stress is in the same location as the TET and hexates. And we're actually getting a stress that's very similar. And also, finally, we can show the deflections. Here, we'll go ahead and scale this up to 10. Well, let's do 10. And show that in the model as well. So, how does this compare against the TET mesh in the model, and the hex mesh and TET mesh for both stress and runtime? Well, the first thing we're showing is that our mid-surface mesh is actually getting a very similar stress to the hexate. And in this case, we're likely using this because we're not likely using this model to define global structure sizing. And because we're not really worried too much about the through thickness compression, those differences do not make much of a difference between our hexate and mid-surface. And where does this really come into play on its advantage? Now we can see here our maximum displacements. We're within about 50 thou of the hexate model. And the reason for that is because we're not including the through thickness properties. But the big thing is the runtime. We have over a 10x reduction in runtime from a quad 4 to a hexate. 39 seconds as opposed to 503 seconds. And this is really powerful. The other thing too is because all the thicknesses are analytical in the model, we're able to actually modify those thicknesses very quickly on the fly. We can update the property and update the element thicknesses to possibly include, better thickness regions in this part of the model. So overall, we're showing that especially for a thin-walled structure like this, that using a shell mesh is definitely the most cost-effective time. It would save you a lot of time in being able to iterate between models. All right. One of the questions that came in here is, does updating element thicknesses to solid automatically generate new properties? No, it does not. It actually will go ahead and change those on the, it will use the same property and it updates the element thicknesses. There might be some other tools there are other tools for generating separate properties. So there are other options. We can definitely discuss offline on that. And David already answered the next question, which is, will it work with Inventor? And David would know since he wrote anyway, Nastran. All right. In the interest of time, we're just going to show a little bit more in post-processing, since we only have a couple more minutes here. What we're going to show here is the power of the post-processing toolbox in the model. We've already shown some of the options here. One of the key things might be is your interest in trying to get this information out to Excel. One of these options is the data table. So many times you might be using this data for other solvers, like perhaps pulling information to calculate margins or fatigue calcs or other information. Sometimes in previous times, you'd spend time looking at the contour, writing down the number and for each output set. But here we can use the data table to quickly grab that information out of the model. So I'm going to go ahead and turn off thicknesses just to be able to highlight some stuff here. And we're going to go ahead and look at the model. We're going to grab, some elements in this region and just populate the data table. We'll add a couple results here. I might be interested in the plate and top bottom von Mises stresses. Here we have a interactive, I'm going to pull this out so we can see it a little bit better, a very interactive tool for being able to organize your data, whether you want to organize by element stresses, by property types. You're able to pull data in and out very quickly. Here in this case, I might be interested only in the ID and stresses here. And we can interactively use this in the model here. So let's say we sort by peak stresses in the model, highlight, and this will highlight the elements in the model. So you can see here, based around our selection, let me go ahead and, oh, that's why, let's go to the bottom. We can see where those stresses might be in the model here and highlight them on the fly very quickly and easily. The other thing we can do is we can export this very quickly to Excel. Here, I already have a margin table that I've set up where I will go ahead and I've hit copy to clipboard. I'm going to paste that down. Go ahead. I forgot to add a little ID here. So let's go ahead and add the property ID back so we have the row count correct. Come back to here, copy that down, filter through, and we can automatically have this calculate for margins. This is useful, for instance, for fasteners and other aspects, or our other tools that you might be working with. One last thing we're going to show here is the free body tool. The free body tool is a very powerful tool in the FEA set here. So the free body tool allows us to do sum the forces across an interface. So for instance, here we would set this up by doing new free body, specify the type of conditions here. And in this case, we already have two that are set up. Here for this interface load, we're going to grab the elements here. We're going to grab the nodes along the surface here. And from this, we actually get the interface force of 2,500 pounds. Now this makes sense because this is a simply supported beam throughout the model. And what's nice is we can save these and for all the different iterations, run this information and be able to extract this through the list output force balance command to grab across many different output sets. Another tool we have with the free body tool is the section cut. So what the section cut tool does is you define a plane. So here we have the plane defined. We've actually limited it to a certain group of elements here. So I'm going to show that element group here. So we're only looking at the elements along this group here. Here we'll specify the plane normal. And we can quickly look at information such as what is the bending moment across the structure here. So, and we can dynamically slide that across the model. So maybe we're interested in seeing what it is here or further up in the model. And we can actually list this data out to a data table. So using the data table command earlier, we'd be able to generate this data right on the fly. Oops, select the output. Oh, I need to turn on the data table. Grab our output set. And here we're generating the data for our surfaces here. Now I've actually gone ahead and went further and did this for 500 points on the model. And so we literally are just plotting the information here in the model. And we've generated our plots here, which we have in our presentation here. So here we're just showing the differences between a point load, so simply supported beam from a point load. And here we can see the distributed load because the fact that that block has a little bit of surface to distribute the load across, for a shear diagram, and also a moment diagram, again, comparing our theoretical of a point load versus the actual FEM load. Now, this is useful in cases of where maybe you're interested in the shear moment diagrams of your wing spar, and you want to focus on a specific wing spar section. You might have a forward and aft wing spar, for instance, and so you want to see how well your CFD pressures from your FEM load were applied to your model versus your theoretical sizing that you may have done. So this concludes some of the post-processing capabilities. There's a lot of capability in FEMAP for post-processing. So what have we shown today? We've shown how for solid meshes, we've shown that the hex dominant mesher is really able to create high quality meshes quickly and easily. We've essentially replaced the TET mesh for complex solid geometry in our models. So this is a really powerful tool inside your model for solid meshes. Now, many times you may not need these solid meshes and you want to be able to run much quicker with iterations. This is where FEMAP is a really powerful tool for working with mid-surfacing, being able to control your mesh directly and dynamically and create your surfaces, and then also be able to use your solid geometry as a reference for creating your mid-surface geometry. Finally, we were showing some of the post-processing tools within FEMAP, showing how we're able to both interactively and quickly post-process your model inside FEMAP through the contour plots and controls, as well as outside of FEMAP, such through the data table and free body tools. So at this point, I'm going to go ahead and hand it back to David to conclude our webinar and kind of review our main points.
Thank you, Andrew. Very nice. I just want to clarify one thing. FEMAP, as far as support for solvers, supports Autodesk Nastran very well. It was NEI Nastran in the past, and we had a great relationship with Siemens. So there's a lot of integration in there. The cool thing about FEMAP is it unlocks so much capability that you do not have with Inventor Nastran, because the core solver can be disconnected in Inventor Nastran and used directly with FEMAP. So just adding FEMAP unlocks tremendous capability, including all of that meshing that we just looked at, and the hex meshing, which is hex dominant, that includes pyramid elements and everything else. All of that is supported in Autodesk Nastran. For the conclusion here, mid-surfacing provides a means, obviously, for dramatic performance improvements. We saw that not only is it 10 times, it's really 100 when you compare it to the Hex 20 and the 10 meshing. When solid meshing is more applicable, obviously the FEMAP hex dominant mesher provides high quality and more automated control. We all saw how quickly Andrew did that. I will tell you honestly, yes, it does take longer to do the meshing. The TET 10 meshing is much quicker, but it's not dramatic. It's like, okay, maybe 10 times, 20 times longer, but given what it does and the quality of the result and how much time it saves you versus the traditional hex meshing techniques, it's well worth it. And at the end here, Andrew showed you the depth of the post-processing capability in FEMAP, which is unparalleled as far as results. Anything you possibly could want, and there's a lot that he didn't have time to show you, you can get through FEMAP. Thank you. So now we have time for some questions. Whoever wants to stay on, we're willing to stay here and answer the questions. Okay, so somebody asked, how often does SDA give FEMAP webinars like this? Andrew, I'll let you handle that.
So quite a, every couple months we'll give a FEMAP webinar or some other webinar, maybe some other topics of other software packages um, we use. And maybe throughout the future, one of the things we will probably try and do here soon is we might try and do maybe even a couple more tips and tricks focusing on some of those capabilities. We've given a lot of what's new webinars or specific other applications as well.
Yeah, and we'll be doing more detailed webinars, especially technical ones. We're going to vary them, depending on the audience, but we'll be doing some that'll be very technically oriented, detailed oriented, as well as other ones that'll be more general in nature. We have another question here for you, Andrew. In the free body section tool, tends to grab nodes outside the cut plane even after adjusting the tolerance and search radius. Is there a way to limit this behavior?
Yeah, so I assume you're probably referring to the fact that, for instance, if I were to free body cut through here, I'm going to be grabbing all these parts. One of the things that I did in this particular case was I actually limited this group to these elements. So you'll see here, if I click on the highlight, I have a specific free body group. And I kind of went through this real quick just because we were pushing time here. But one of the things that's kind of hidden in here, if you go entity selection mode and go to group, you can actually limit your nodes of what you select and want to see in your model. So in this case, you might actually limit it to a single spar, for instance. You might be going, hey, what is the load, the shear moment tension, or sorry, shear moment torsion on my forward spar versus my aft spar. So this allows you to kind of be able to do that. And I've actually used this on several programs I've worked on very extensively. So hopefully that answers that question.
Okay, another question here. This one is the auto hex meshing. Any plans to improve the capability to control the location of pyramids? I want to say something first. The pyramid element is actually not a bad element. If you look at it, I don't have any indication that it produces a inaccurate result, even in a linear form. There's so many options. You can always do hex 8, and then it'll transition the hex 8s to parabolic pyramids. So you don't have to use non-parabolic pyramids. But maybe Andrew, you know more about this.
Now, I was actually going to say this is something, this would be an excellent question to the FEMAP development team. And as mentioned earlier, we are in contact with them routinely. And actually, even before this webinar, we spent time with Mark Sherman, one of the lead developers of FEMAP from the beginning, talking about some of these things. So these are definitely some good questions I'll definitely bring with him and chat with him very soon.
Okay, and then this other question here is, what is the difference in the number of elements used between shell and hex meshes? So let me just say this. You could obviously go in this model and 5 times the number of shell elements than we used. There would be no problem with that. And then your solution time, instead of it being 40 seconds, it might have been 2 or 3 minutes. Okay, it wouldn't have made a traumatic difference. That was just something that we defaulted to, and relatively the same size element proportionate to the solid elements that we're using. But there's nothing that says you can't use a finer mesh. In fact, that's one thing you could do with shells, because they are so more efficient than the solid elements. You could over mesh, no problem. And then a nonlinear webinar, yeah. So the best thing you guys can do in the audience here is to email what you want to us and tell us what you'd really like to see. And we get enough people that agree, we could certainly put a webinar like that together. As far as nonlinear webinar is concerned, there's a lot of nonlinear. It's like, okay, are we going to talk material nonlinear, large displacement, contact? What particular behaviors do you want to see in nonlinear? And then we could talk about that. Then we have another question here. I work with fully detailed injection molded parts, which often have drafts and fillets. Is the mid-plane generator worth looking at for these detailed parts? All right, Andrew, you can have that one.
Yeah, this is actually related to, I saw another question of asking why would you not always want a mid-surface? So this really depends on your application. Earlier, and I'm going to go back to this slide just to show that. David showed kind of the difference between like a solid block like this piece versus the skin stringer frame section of an aircraft. In this case, it depends on your level of detail. For structures that you might be worried about or that are large solid pieces like this, mid-surfacing really doesn't apply. To try and really idealize a mid-surface, for instance, here, probably wouldn't apply. Same thing, maybe like, for instance, there might be a small bracket, a large thick bracket that might be holding, at the wing joint here, for instance, on this Cessna. That might be something that might be of interest. So that might be a case for other parts that might have a lot of details, such as draft and fillets. You might want to move to the hex dominant mesher, just because you might be wanting to capture those through thickness stresses, and that's one thing that is a disadvantage for mid-surfacing elements. Their speed means that you're eliminating a degree of freedom of the through thickness stress. Areas you might be very interested. There have been times I've actually created some very detailed preload models where I'm interested in that through thickness stress, and that would be a direct application right there of using a solid mesh over your shell mesh. And if there's other questions, definitely feel free to email us on that, and we can definitely talk more for your specific applications.
Okay, so the next one here, how many individuals are you aware of pairing FEMAP with Autodesk Nastran? Well, let me give you some history about that to answer that question. It goes back to NEI was acquired by Autodesk in 2014. So the bulk of the NEI business was FEMAP and NEI Nastran. NEI Nastran became Autodesk Nastran. Autodesk promoted the product as the InCAD Inventor product, and then eventually the solver part of it was disconnected so that you could run Autodesk Nastran separately. When you install the latest version of Autodesk Nastran, you have 3 individual modes. You have the Inventor Nastran that you get the editor, and you also get the command prompt where you can just run Nastran from the command prompt. So the answer is hundreds, possibly thousands of individuals are using that in that mode. Many with FEMAP, I would say they're continuing to do that. People are switching over now and adding FEMAP that are just purely Inventor Nastran users because of the advantages of using FEMAP that I think we showed in this webinar, especially the hex mesher, which is state of the art and a real game changer for productivity, and also the mid-surfacing capability, which as well is very capable. One of the cool things about the mid-surfacing that Andrew was showing was the fact that if you have a thickness variation when it mid-surfaces, it captures that. And that is really powerful. I don't believe Inventor Nastran does that. And then the next question here is, what software apps does SDA a reseller of? And I'll let Andrew, you talked about that in the beginning. One of the ones that's not mentioned in the list there is Adena, unless I missed it.
No, it's not listed. Adena is also another nonlinear solver sold by Bentley, and is also another very capable code that's integrated. Also, it integrates well with FEMAP. You might those who've had a keen eye may have noticed the Adena button clicks here as well. But that is another software package that we support in addition to the Siemens products here.
Yeah, and it's a very capable product. I'll just tell you that right now. Siemens had a very good relationship with Adena until Bentley bought them, which obviously created a problem, but it is definitely a very good nonlinear code as well. All right. Any other questions? We really appreciate these questions. And also, we really appreciate the 70 people who have lasted this long into the webinar. Thank you.
And I did see a question asking what are best techniques for transition to shell to solid and shell to beam elements. There's a lot of different ways of connecting these. For instance, for shell to solids, there is some of the contacts we did show are some of the glued contacts. There's that option, and there's also rigid elements. This might be a great topic for another webinar, or if you do have further questions or a specific application, definitely send us an email.
All right. If that's it, I want to thank everybody. We're going to be emailing all of you with the link to the recording at the end here. And please feel free to get back to either one of us with questions that you may have. You have our email addresses here that you forgot to ask or didn't have time to ask.
All right, thanks very much, guys. We'll
Thank you.
look forward to talking to everybody soon.